Huh?
As well? Will you upload the completed slides?
They are uploaded already.
Oh, okay, the completed version?
Yeah, there's a completed one as well. It was from the earlier class, but it's going to be hopefully the same answers. So last time we did all of chapter 8 in one lecture. So what I wanted to do is make sure we had some activity to show you how I want you to use these things. And so the idea is that you need to know your chemical formulas, both forwards, backwards, and in the middle, basically, so that you can understand how they're going to be asked for you on the test. So once you filled out your table, your reaction table, which I'm sure you all spent lots of time doing that over the weekend, but we're going to go over those reactions that are on that reaction table. And the quiz on Wednesday is only over chapter 8. Okay, it's only over chapter. We're going to start NMR today, but I have an activity for that before I want to quiz you on that. So we're going to do this activity today, and then we're going to start NMR. So the idea here is that I want you to learn these reactions the forward way, which is reagent and substrate, and give me the product. And then I want you to have the product and the reagent and figure out what the starting material was. And then I want to give you a starting material and a product, and you have to fill in the reagent. Okay, so if you know the reactions all three ways, that does three things. Number one, it means you understand what the reaction does. Number two, you're going to have to do multi-step synthesis through the rest of organic chemistry and in organic chemistry too. So this will help you figure out how to do retrosynthesis. And number three, it'll prepare you for the exams where I can ask you the question in any of those three ways. Okay, so the first way is the way we kind of looked at it. We had the substrate and then we had the reagent, right? And so what we'd be able to do from this is we'd be able to say, okay, we have chlorine, we have carbon tetrachloride. What's carbon tetrachloride? It's the solvent, and it can't be halogenated. So because it can't be halogenated, it will not react with our chlorine. But so we're going to do that. And so we know that our chlorine is going to go adding across here because it's a double bond, and that's what it does. So when we draw our product, we're going to draw everything up to there and go chlorine and chlorine. Now, they did add anti. Remember that they add anti because you get the chlorinium cation on the top, and then it has to come in from the bottom to do the other one. Okay, but we have a free rotation here, so you don't have to worry about stereochemistry. Okay, now this is a chiral carbon. So we're going to get a mixture of R and S for that chiral carbon, because if it adds across the top, it gives one isomer. If it adds across the bottom, it gives the other isomer. So the R and S has everything to do with that, and that's why it's going to be anti-addition, and it will have mixed stereochemistry. So, okay, so what's going to happen in the next one? Okay, so let's see, we're going to have something attack the double bond, right? And it turns out we're going to have the mercury attack this bond right here, this part of the carbon right there. And then the water is going to end up attacking this one right here, because that's going to give the more stable carbocation intermediate. But because the mercury is attached here, it cannot rearrange. Okay, so we know it's going to be there. And then we're going to reduce the mercury off. So that means we're going to have an OH here and a hydrogen here. So let's draw our product. We're going to have our OH here and a hydrogen here. I'm going to draw the hydrogen because we actually removed the mercury to put that hydrogen there. So that did change. That is a new hydrogen to the molecule. Okay. So our next one here is bromine in water. Ooh, so we're going to get almost the same product as this, right? As the top one? No, that's the halohydrin reaction. Okay. So what's going to happen with that is, let me do that. Is we're going to have our bromonium cation form first, Br plus, and it's going to have Br minus as our nucleophile, okay? If we had it in carbon tetrachloride, that's the only nucleophile we have. But we have water, and water has two lone pairs on it, and it can act as the nucleophile, okay? And not only does it act as the nucleophile, it is also probably 1,000 or 10,000 times more abundant than the bromide ion. Because we've only made that one bromide ion, but we have the water, all the solvent around it. So it's going to react quickly, and it's going to react on the more electropositive side, which is the more substituted side. So we're going to get, our product is going to be OH and Br, again, anti-addition, but again, we have free rotation there, and so we're going to get a mixture of isomers at this stereocenter. Right there. Okay, questions on that? Yes.
Is the mercury always going to add to the less substituted?
Yes. Yeah. Oh, also, by the way, if you haven't already seen it, I put a video of all the mechanisms in the chapter together. They're pictures from the mechanisms, but I talked you through them to figure out where things add. Okay. All right. So let me erase this and just give the answers there. All right. Okay. Now next, we have these. So these are reactions we played with over the weekend, I'm sure. I know I did about 30 of them just for fun on Saturday morning. Anyway, so we have HBr. So H is going to add here, Br is going to add there. So our product is, we don't have a double bond. And so the bromine is going to add here, and the H is going to add here. And again, that H is new to that molecule, so I added it there. Okay, so by knowing what the reagent does, and a good way to do it is to actually say, okay, wait a minute, this is going to add to here, and then the hydrogen is going to add here. And if you draw it like that, oops, not bromine. If you draw it like that, then when you get to the other side, it's like, oh, the hydrogen's here. So that means the OH is going to be over here. So you have that reaction. So this is the hydroborination. And remember, that's also adds syn, because the hydrogen and boron react at the same time across the double bond. They just all exchange electrons, and we get to our boron there, but then we oxidize it off with the peroxide, giving us our alcohol in that primary position. It's the only way to get a primary alcohol. Okay. Oh, now let's have this. Water and trace acid. It can also be, you know, H2SO4 or something like that. So what's going to happen here? Well, let's see. Something's going to happen. We're going to add a proton to this. So the first thing we're going to do is we're going to add a proton to this, and we get a carbocation right here. Is it going to stay there? No, because there's a possibility of having a carbocation here. And that's what's going to happen. It's going to do a 1,2 hydride shift. And it's going to make the carbocation here. So now the water can attack it and then lose a proton. And therefore, we are going to end up with a tertiary alcohol from our 1,3. So see, the forwards are not that bad. We were going to kind of look at them and see how they go. But what about backwards? I'll come back to these, by the way. Let's do it backwards, okay? So let's say we had HBr and we had this right here. Okay. So I think we got two choices, right? We could have a double bond here or a double bond here, okay? But only one of those is going to give one isomer. Why? If we have the double bond here, we could add the bromine to this side or this side because they're equal. There's no more substituted carbon. So we get a mixture of the 2-bromo and the 3-bromo product. So that means this wouldn't be the substrate we'd use because we only have one product here. So that means it has to be the outside one. Okay, and if we draw that right here and then have the double bond there, this one is only going to give bromine attacking here, hydrogen attacking here. Because it is, this would be a secondary carbocation, so it's not going to move. It's just going to give us that one product. Okay, see how we're looking at it backwards, where that double bond had to be to get just this one product. Okay, let's do it again with the mercurization, demercurization right here. So that means we had to have our mercury on our less stable substrate. So that means our mercury had to be, here. The mercury had to be here. It couldn't be here because that's where the OH goes, right? So that means the mercury had to be attached. No, I'm sorry. The mercury had to be attached, here because it sets up that intermediate where it has a partially positive carbon and the water comes and attacks that partially positive carbon. Okay, so the mercury had to be here and then we reduce it off and the mercury goes to a hydrogen. So that means we had to have our double bond here. The mercury was here and the OH, it could have been here, but then we would have a mixture of alcohol both here and here because there's no specificity between those because those carbons are equal. So that means it had to be the one on the outside. So our product is 1, 2, 3, 4, 5 with an ethyl group. Notice how a lot of these I'm just using the same substrate because I want you to recognize the change. Don't get caught up in all the stuff. Get caught up in the change. What's changing and what to focus on. Okay. Okay, let's do permanganate hot. Okay. And oh gosh, we have there. So another thing we have to do is, especially when you do cleavage reactions, is you need to count the number of carbons you have. We have 1, 2, 3, 4, 5, 6, 7, 8. So our starting material has to have 8 carbons. Okay, so let's go 1, 2, 3, 4, 5, 6, 7, 8. Okay, and let's see. 1, 2, 3, 4, 5, 6, 7, 8. Oh, I have too many. One too many carbons. Okay, so that means, and our double bond has to be here. Because when we clip that double bond right here, we're going to have a 7 carbon fragment and a 1 carbon fragment. So it has to be on the end like that. And it's going to give us the carboxylic acid here. So we knew it was going to do a cleavage on that double bond, and we now know how many carbons are in each fragment. So that means we have what the starting material was. All right, questions on that? Okay, so let's do a couple more backwards. Okay, Lindler's catalyst. What did we have to start with? Okay. Well, we ended with an alkene. So we must have started with an alkyne, right? So this is technically chapter 7, but let's count our carbons right here. 1, 2, 3, 4, 5, 6, which means we have to have 1, 2, 3, 4, 5, 6. 6 carbons in our product. And remember, Lindler's does syn addition, so these are hydrogens here. That's why it's the cis alkene. Okay. So, let's add 1 equivalent of HBr right here. So again, what do we have to start with? We had to start with an alkyne again. And it's 1, 2, 3, 4, 5, 6. So it's actually the same substrate. And here we started with 2 equivalents of chlorine, and that gives us our tetrachloro material, which actually ends up giving us the same substrate. Okay. So this is the second way I can ask the thing, saying, okay, here's a product. Here's what you want to make. What did you have to do to make it, right? And so, and I told you the reagents you could use. So that means there's only one starting material you could have used to make that product. Okay, questions on that? Okay, let's go over the other one, the middle. What reagent do you need to take cyclohexene and turn it into potassium, the cis alcohol? Really toxic. The osmium tetroxide. Osmium tetroxide and pyridine. Right here. That's going to give the osmate, and then the second half of it is the sodium hydrogen sulfate to break it off in water. Okay. So that's pretty interesting. We can do that. That's pretty cool. Let's look at the next one. Ooh, we have a hydroxy bromide. All right, that's probably a halohydrin reaction. So we'll have to have bromine to create our bromonium cation, and then we have to have water in there to attack it, to give us our out. So see how you can define what reagents to use just by looking at your reactant in your product. Here, we're going to clip this off right here. So that means we're probably using potassium permanganate, O8 hot. Right there. And so that's going to clip our double bond and oxidize these two aldehydes that we formed first down to carboxylic acids. We have 1, 2, 3, 4, 5, 6 carbons, so we didn't lose any carbons. So that's neat. If you have ring structures, you don't lose carbons because they're at the two ends of your species. Okay. All right, let's try this one right here. What would you use to make that? We'd use bromine, right? That's all we need for this, right? No water, just bromine. That doesn't look right. Shouldn't there be 2 bromines on it if we use bromine? Oh, so it can't be bromine. So it must be HBr. And the H is going to add here, and the Br is going to add to the more substituted carbon, and boom. Okay, let's see. Double bond. Wow, that's really hard here. Ooh. Water and acid. It's going to give protonation here first, the least substituted carbon, and then it's going to give our OH here. So that's a good way to do it. Oh, this is backwards. Actually, this needs to be, it's the double bonds here, actually. So how do we get that? We have a primary alcohol. There's only one way to get a primary alcohol. Borane as our first step, THF, 2 peroxide in water with a little bit of base. Okay. See how that's another way to ask the question, and it's a way to, if you know the equations forward, backwards, and in the middle, you're going to have a much better chance of making a good grade on the quiz on Wednesday. Don't forget. All right, so let's do those last few just so we have some more reviews on how to do things. Oh, that's a weird one. I didn't go over this in class, but it's in the book. So actually, I think I mentioned it in class too. Permanganate cold. Turns out that's the other way to make a cis diol, permanganate cold. If you heat it up, it's going to cleave that double bond. That's how we get to the carboxylic acids. But permanganate cold is going to give us our cis diol. Cool. So now we know another reaction forward. What's going to be the product of the next one? Are we going to have a hydrogen added somewhere? Well, it's catalytic right here, and it's got some conditions here. So that means it's probably going to reduce down all of the alkenes to alkanes, and we're just going to have this hydrocarbon. Ooh, bromine and methanol. That sounds like a freaky halohydrin reaction, right? So the first thing we're going to do there is we're going to make our bromonium cation right here. This side's slightly more positive than this side, partially positive, which means the methanol now can react. Instead of water acting as the nucleophile, the methanol is reacting as the nucleophile, and it's going to substitute the more substituted side. So that means our product is going to be OMe Br. So we're making an ether. So if you use any protic solvent, it can act as a nucleophile once you formed a carbocation or partial carbocation. And in this case, it is regioselective because it's going to go to the more substituted carbon. The water is always, or the core nucleophile is always going to go to the more substituted carbon. All right, questions on that? Okay, so let's do the last of them and remind ourselves with that. Oh, osmium tetroxide, that's going to give us a cis diol. OH, OH. Ooh, bromine and carbon tetrachloride. It's going to add across the double bond. We don't have any water, we don't have any methanol, so we're going to get 2 bromines on there. Br, Br. And again, this is a chiral carbon. This is a chiral carbon. In both of these reactions, you're going to get a mixture of R and S because one is syn addition, but if it goes by one, the bottom, it's going to get one isomer, and the top, it's going to get the other isomer. This one goes by anti-addition, but if the bromine binds at the top or the bottom, the first bromine controls where the other bromine has to attack. And so that's going to give us an isomer. Right there. Okay, and permanganate cold. These are the hard ones because you got to remember that when you have the double bond, you're cleaving this double bond, which means your product has 1, 2, 3, 4, 5, 6 carbons in it, plus CO2. So we have to go put our carboxylic acid plus CO2. Okay. All right. You see how you need to study these reactions forward, backward, and in the middle. Okay. Did this help? There's a blank one of these online to help you practice, and then there's an answered one online already. So that it'll have hopefully the same answers. Okay. Questions?
Would you be able to repost it, not the activity thing? Because for some reason I can't see that activity.
Okay, I will repost it under, yes, I will repost it. I won't be able to do it till about 5 p.m.
That's fine.
Okay. All right. So now we're going to move on to chapter 9. Okay. So these are what we're going to talk about today is nuclear magnetic resonance spectroscopy. It's nuclear, not nuclear. That president said it wrong. It's nuclear. Okay, so make sure it sounds similar, but they're different. Okay. And then we're also going to do some mass spec. Okay, so when we have magnetic resonance spectroscopy, it actually is a really cool tool because it gives us our carbon-carbon bond connectivity and skeleton plus our carbon-hydrogen frameworks. Okay, so it means we know where the carbons are and we know where the hydrogens are by that. And so we have a really good idea about what's happening in simpler molecules. Okay, the most common of these is what we call 1H NMR, which we call proton NMR. Okay, just like when we used acids and bases, we call that hydrogen or proton. We're going to do that proton. And the 1 means it's the isomer, it's the isotope that only has the proton. Okay, it's not deuterium, which would be 2, which has a proton and a neutron, or tritium, which would be 3, and have a proton and 2 neutrons. So we're going to use that one there as one of our things. And then the other one we use a lot is carbon-13 NMR. So in carbon-13 NMR, the most common element isotope is 12, right? But there's about 1.1% of carbon-13 naturally abundant. And then there's even more, there's some carbon-14, which is radioactive and slowly decomposes. And that's how we can radiodate things. But we want to use the carbon-13 one. So one of the interesting things about that is we need that mismatch in things in the nucleus. We need an odd number of things in that nucleus. And so we're going to use a source of radio waves. These are very long waves, very low energy and frequency. But the reason we're doing that is we need to knock the nucleus. And so when we looked at IR spectroscopy, that was enough to excite a bond. That was a much bigger energy. Here, all we're looking for is to flip around our nucleus. Okay. So in these low frequency waves, they interact and change the nuclear spin of elements that have typically an odd number or an odd number of an odd atomic number, but an even number of things in an isotope with an even number. So that turns out that with hydrogen, it was atomic number 1, but as the 2, it has it is also NMR active. Most commons are hydrogen, carbon, fluorine, and phosphorus. Okay, so let's take the roll and then I'll tell you how it works. Yeah. We have about 20% of my students live. you might want to try to come and take the exam 3 live in person for you guys at home, just so that you can get used to filling out Scantrons, because the final exam must be in person, no other way. ODF students can take it at the testing center, but you better get that reservation soon. Okay, so what happens with the radio waves is we have a huge magnet, and all of your nuclei are spinning around. So they have poles, like positive and negative, right? And so they have spins. And so what they do is when you put it in this huge magnet, it lines them all up, either with the magnetic field or against the magnetic field. And they're all parallel. And what happens is you hit these with radio waves and it knocks them out into a higher energy state. And then you listen for it as it kind of rotates back and goes, thunk. There's different times it'll do different things. The more shielded it is, the more electron density it has around it, the quicker it goes. The more de-shielded it is, the less electron density it has around it, the slower it goes. And so we can see the spatial difference in our spectrum. Okay, so what's the most important thing about NMR? Proton NMR, you need 4 things. Number of signals. So you need to figure out what that means and how to get that, and you can predict it. Intensity of signals, and what we mean by intensity. Position of signals, so where they are on the x-axis, and spin splitting of signals. Okay, you don't have to know every single one of these to answer the question. You actually can use 2 of them or 2 to 3 of them. You don't have to know all 4 of them perfectly to get it done. And of course, if you put it backwards, it's still spin. Anyway, so these are the only things you have to worry about, okay? So let's look at a typical spectrum and figure out where we can find these 4 pieces of information. So this is, again, like the 4 answers the 4 questions you need to ask yourself when looking at an animal. Okay, so the chemical shift is the x-axis, and it's increasing to my left. Okay, you start at the right side is where the 0 is, and it increases. Okay, so this is 0 right here. Now this is an internal standard, and we'll talk about that. It tells you where 0 is. Okay, now so that is shift. So that means this is in a different position than this. Okay, so that's shift. This is a peak, and this is a peak. So that means we have 2 kinds of hydrogen. So we have 2 types of hydrogen in here. So we're going to have 2 signals. Okay, and this is splitting right here. This splitting pattern and this splitting pattern will show you exactly how many hydrogens are on adjacent carbons. Okay, and the intensity, which is not actually by how big the signal is, right here, we're going to actually integrate this and figure out the area under the curve. Because if you think about this, so if you look at the area underneath all of this, it might be more or less than the area under here. You can't tell because it's spread out over more peaks. So what we're going to have to do is we're going to have to take an integration and say, oh, this is 2, and oh, this is going to be 3 hydrogens. Okay, so that's what we mean by intensity. Intensity is what does the integration show. Okay, so those are the 4 things. We have number of peaks, 2, shift of peaks right here. We have intensity given by the integral, and we have splitting right here. Okay, so let's look at another spectrum and figure out what we mean by the shift. Okay, so carbon NMR usually is very sharp peaks. There's only a couple things that aren't sharp peaks. Okay, and the chemical shifts increase from right to left. And when we say that, we want to say things that are closer to 0 are upfield, smaller numbers. Things that are further away from 0 are what we call downfield, larger numbers. The way to remember that is up only has 2 letters in it, so it's smaller than down, which has 4 letters in it. So upfield is smaller than downfield. So think of it that way. If you're not an upstage or downstage person, or downtown, uptown, if you're from a big city, same kind of thing, smaller numbers uptown, bigger numbers downtown. Okay, and all of these are done on a relative scale to an internal standard. And this is tetramethyl silane. So tetramethyl silane looks like this. It's a silicon right here with a CH3, 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 and CH3. Okay, and so what we have here is that silicon actually takes just a little bit of electron density away from each of those carbons with hydrogens on it. And so that is below wherever we see most of our organic compounds. Just having that silicon there pulls a little bit of electron density from the carbons and gives us our 0 point. Cool thing is we use the exact same internal standard for carbon NMR. So these carbons are 0 right here in carbon NMR, and these hydrogens are 0 in hydrogen NMR. Okay. And almost everything is downfield, higher number than TMS. There's only a few things that are below 0 in hydrogen NMR. Okay, so now let's talk about number of signals. Okay, number of signals is kind of a crafty thing. It's the number of different kinds of hydrogens. And by kinds of hydrogens, I mean hydrogens with different electrical environments. Okay, so let's look at this one right here. And what do I mean by electrical environment? I say, well, you know, we have all this pushing and pulling from polar bonds, right? And so we need to look at that. And then there's also some through space interactions we need to look at. So the first one here, we have a carbon with 3 hydrogens and an oxygen. Okay, so that's its electrical environment, all the things that are directly bound to that carbon. Okay, so that gives us a signal. Those 3 hydrogens give 1 signal. Okay, now let's look over here. We have a carbon with 3 hydrogens and oxygen. That's exactly the same electronic environment. So that's exactly the same electronic environment. So that means it has the exact same signal, which means we have 1 NMR signal. Okay, let's move these bonds around a little bit and do CH3, CH2, and OH. Okay, so let's think about how many different types of hydrogen we have. We have a CH3 bonded to a carbon. So I think that's a signal. We have a CH2 bonded to an oxygen on one side and a CH3 on the other. So that's not the same as any other hydrogen there, right? So this is going to give a signal. And we have this. This is a signal. So we actually have 3 signals here. Okay. So what about this? How many signals do we have here? That's an H, that's an H. So these 3 hydrogens right here are different than those 2 hydrogens. So we're going to have 1 signal here, 2 signals there, and a second signal here. So this one's going to have 2 signals. So do you see what I mean by different electronic environment? Okay, so kind of just look at what it's bonded to, and if 2 of them are looking pretty close, you might want to look at it again. Now you got to be careful when you do that because, because when you have cycloalkanes, let's say you had this cycloalkane right here, and you're going to go, oh, well, that just has, let's see, there's a hydrogen here. So that all these hydrogens look the same, and this hydrogen here is the same. So we're going to only have 2 signals, right? I'm not sure about that. Let's redraw it such that it's 3-dimensional. And we're going to have let's have our chlorine up here and our hydrogen down here. And then our hydrogen, 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 and hydrogen. Okay, so obviously this hydrogen is its own signal. So that's 1. These hydrogens are not the same as these hydrogens up here. Why? These hydrogens are different than the other hydrogens because of their proximity to the chlorine. These, the other ones, are only next to another hydrogen. So I said there was through space interactions that will change the electronic environment as well. So that means this actually has 3 signals, 1, 2, and 3. So it's important to draw those out. What else is important to draw out is alkanes. Because if you just put Cl, you're going to say, oh, well, that's just 2, because you got those 2 hydrogens on that one side. These look the same. These 2 over here look the same. But they're not because of our through space interaction. This hydrogen sees a hydrogen. This hydrogen sees a chlorine through space, which means we have 1 signal, 2 signals, 3 signals. So even on such a tiny molecule as chloroethylene, we have a difference in our system. And so we have that. Okay, questions about number of signals. Okay. Let's do a little more practicing right here. So in this one right here, well, we have dichloro. So, okay, so it turns out this one has that through space interaction, this one has that through space interaction, and they're both on the same carbon. So they are equivalent. So they have one thing. What if we did this? Oops. Okay, so there's still 2 hydrogens on the same carbon and we still have electron withdrawing groups nearby, but this one sees bromine, this one sees chlorine. So we have 2 signals. And again, these 2 hydrogens over here look the same. They're on the same carbon. They have the same electronic environment, but through space interaction gives us 3 signals. So do you see how we get our number of signals? Difference in electronic environment. Okay. So now let's talk about position. Take a drink of water real quick. Okay, so position is kind of weird. It says that basically the electron density near the nucleus shields it from the magnetic field. So the more electrons you have on it, more electrons you have near it, the more it does. So I guess that means that silicon was donating electrons to those carbons, right? So that they have more electrons around them, bringing them down to 0. De-shielding is when the nucleus absorption is at a higher frequency. So that means that you have something with electron withdrawing group that is pulling electron density away from that carbon, which pulls it away from the hydrogen. Okay, so that means that things that have things bonded like oxygen and nitrogen next to them, those are going to be moving downfield. Things with double bonds are going to be moving downfield. Things that are acidic are going to be moving downfield because they're going to be more and more shielded. So the protons near nuclear atoms are de-shielded and therefore absorbed downfield. So that means you don't even have to memorize the numbers. You can if you want. They're in the book. There's a big table. Okay, but I want you to look at it this way, of looking at the chemical shifts this way. Okay, so what we do is we start at the end here, and of course our 0 is TMS right here. Right here is our TMS, tetramethyl silane. And then we have our hydrogens on hydrocarbons. No electronegative atoms around at all. And the cool thing is the primaries are lower than the secondaries are lower than the tertiaries. So the primaries are actually the lowest, the secondaries are next, and the tertiaries are just a little over. So your primaries can actually start here at 0.8. Right here. And your secondaries can go all the way up to almost 2, about 1.9. Okay. So that's just hydrocarbons, right? But now if you're 3 bonds away from a double bond, these are sp2 hybridized carbons. They have more s character. They are electron withdrawing comparatively to the sp3 hybridized. So they're shifted down again. And that's also true for an aromatic ring or a carbonyl or an alkyne. This is an SP right here. But it turns out it doesn't pull as much as a double bond because of well, I'll show you the next. So all of those are right there, kind of in that 2 to 3 range. Okay. Now we have something special about oxygen and nitrogen. Okay, in IR, we saw broad ranges for oxygen with an alcohol and the amines because of hydrogen bonding. That's the same reason we have a broad range for alcohols and amines in NMR. If they hydrogen bond, they'll have broader peaks and they'll be shifted around quite a bit. You can actually, if you're really careful and choose your solvent correctly so it can't hydrogen bond, you can actually get fairly narrow peaks. So now let's look at this right here. We have the alkenes right here are between 4 and 6.5. And then the aromatic rings, because of resonance, are shifted up just a little bit higher. And then we have the carboxylic acid and the aldehyde. Notice that this is bonded to an oxygen and this is bonded to the carbon. So this hydrogen bonded to that sp2 hybridized carbon with an electron withdrawing oxygen makes this partially positive. And because it's partially positive, it's deshielding almost the most, right? This is an acidic proton. Okay. So let's see how acidity affects it. Okay, so alcohols are pKa 16. Phenols are pKa 10. Carboxylic acids are pKa 5. See how they keep going down and down and down. The more acidic you get, the more deshielded you are. The more deshielded you are, the more downfield you are. The higher the number. Okay, so that's what I'd like to say on that, because what you can do is you can say, well, this one's going to be on this side of that, and this one's going to be on that side of that, just by looking at those general trends on where is it bonded, where is the nucleophilic atom, or the electrophilic atom, sorry. Atom with high electronegativity. There you go. Okay, so let's try that here. So just on that principle alone, should this peak be closer to 0 than that peak, or further away from 0? We have CH3, so that's going to be pretty close to 0. It's going to be like a 1. And we have this peak that has a bromine on it. So that's going to be shifted up above that between 3 and 4. So we see a peak at 3.4. And we see a peak right here between 1 and 2. So this has to be our position here. So this is this one, and this is this one, just by electronegativity. You assign the positions. And then you can then look at, oh, look, that's 3.4, and that's, 1.75. Okay. So we can identify things with just shift without memorizing the table. So I suggest that you don't memorize the table unless you're a memorizer. If you do really good memorizing, there's about 20 things on this table to memorize. What I'd like to do is I like you to get this kind of imaginary picture in your head that as things change, as acidity increases, it moves downfield. As double bonds, or if you have a hydrogen bonded somewhere near a carbonyl, think of it going downfield. Okay. Now, the other thing to look at is this last one here, which I forgot to mention, is if you have a halogen or an oxygen or a nitrogen bonded directly to the carbon, but not an alcohol, you're going to be shifted above that into the 2 to 3 range. So all of your carbons with hydrogens with chloros on it are going to be 2 to 3. Bromine, iodine, they're all going to be in that same general area. Okay. All right, so don't memorize it if you don't want to. I think you can also, just get the relative position based on their electronegativities, and then look at splitting and intensity and number of peaks to get all the rest of the information. You only need 2 or 3 of these pieces of information to solve the problem. Okay. So now let's talk about intensity. Okay. The area under the curve is proportional to the number of protons in that peak. Okay. But we're going to have splitting. So we can't just take the absolute height. We actually have to take the area under the curve. So there's that number of equivalent hydrogens that are relaxing they can actually measure the volume of them. So we're going to do it. But because of those peaks, we're going to do what's called an integration. And so there basically is just, calculus where they integrate under the curve. Fortunately, it's not just the peak height. Unfortunately, it's not just the peak height. It is the integration. And when you integrate, you're going to get a number of curves. And then you're going to see that they're going to be proportional to each other. Okay, so like this would be 50, this would be 50, and this would be 100. Notice those aren't absolute numbers. We can't have 100 hydrogens on a peak. So they must be proportional. So if I divided them all by 50, we'd have 1 to 1 to 2. So we would divide or multiply by the same number on all of them to see if it worked out to give us the same. So we're looking for that proportionality. Most modern spectrometers calculate and plot the value, but if you get some weird number like 1.5, you can't have 1.5 protons. You have to add, you have to multiply or divide by a number to get to all of them being whole numbers and a proportional to the structure you're looking for. Okay, so let's look at this one right here. So first of all, let's look at equivalency. These hydrogens are equal to these hydrogens because even their through space interactions are the same. And then these hydrogens are all the same because their through space interactions and connectivity are all the same as well. So we have 2 peaks. Okay, so, and these are methyl groups. So these are methyl groups, so they're going to be upfield. These are benzene rings, so they're going to be downfield. So we can identify by just the general position. We've identified by where they are, but now we also have how many. We have 4 of these hydrogens and 6 of these hydrogens. Okay. Well, but we have a 1.5 and a 2. I mean, well, 1.5 and a 1. So let's see, we need a whole number. So if we multiply this by 2, we get 3. We multiply this by 2, we get 2. So that's 2 to 3. So that's closer. So let's multiply it by 4 is equal to 4. Multiply by 4 is equal to 3 times 2 is 6. Ooh, whole numbers that match the result we're going for. So you're going to have to divide or multiply to get to those whole numbers that we see. Okay. And so questions on that? So we have, yes.
Those 2 numbers that you just found, do they need to be the same number or just be able to be divisible by each other?
They need to be proportional. You have to multiply or divide by the exact same number on all peaks. So if you have 3 peaks, you got to divide them all by 2 or multiply them all by 4. You can't just figure out a number that looks fun. It's got to be the same across the board because they're proportional. Okay. Proportional. Okay. All right. So now let's talk about spin-spin coupling or spin-spin splitting. Okay. So this is the kind of hardest to understand, but it gives you so much information. Okay. So when we have spin-spin coupling, we're going to take a look at one side of the molecule and say, okay, I'm going to look at no, I need to do the blue. I'm going to look at these hydrogens first, okay? Those hydrogens are on the same carbon, they have the same electric thing, environment, and therefore they have 1 peak, okay? But non-equivalent hydrogens, any other hydrogen that's not that peak, can split it, okay? And the rule is N plus 1. N is the number of non-equivalent hydrogens within 3 bonds. Write that down. The equivalent of the number of non-equivalent hydrogens within 3 bonds, okay? If it's 4 bonds away, we don't care, okay? If it's 2 bonds away, we care. If it's 3 bonds away, we care, okay? So let's look at our molecule here. We would have an integration of 2 because we have 2 hydrogens here. We don't have any hydrogens on this side, and we only have 1 on this side. So our N here is 1 because we have 1 hydrogen within 4 bonds, 3 bonds, So if I drew the hydrogen down here, it would be 1, 2, 3 bonds. So we have 1 plus 1 is equal to 2. So we should have 2 peaks for this carbon. Okay, for B, we should have 2 peaks for B because it is only next to one other hydrogen. So let's do the other one. Let's look at this one here. This is going to give 1 peak. So that's the 1 and the N plus 1. We have a total of 2 hydrogens within 3 bonds. So that's going to give us 2. So 2 plus 1 is equal to 3. So this one's going to give us 3 peaks. Okay, so let's look at what the thing told us right here. And so this is 1 hydrogen. This is 2 hydrogens here. And when we blow up the splitting, we see 2 peaks for this one and 3 peaks for that one. Okay, do you see what I mean by non-equivalent hydrogens? Okay, all right, so let's do a little more in depth here. So equivalent protons do not split each other because they're equivalent. They give a signal. All non-equivalent ones nearby within 3 bonds gives a splitting in the pattern of N plus 1. 1 for the signal and 1 for each of the hydrogens nearby within 3 bonds. Okay, and then splitting can be on the same carbon if there's a reason. If there's a reason, there is a difference. For example, in the case of this chlorocyclopropane, right here, these hydrogens are on the same carbon, right? But they're not equivalent. This one has the chlorine here, this one has this. So this is 2 bonds away. So this hydrogen is split by that hydrogen, and these are equivalent. Oh, let's see, these are equivalent here. And this one's 3 bonds away, that one's 3 bonds away, and that one's 2 bonds away. So we have 1, 2, 3, 4. 1, 2, 3. So this hydrogen is actually going to be split 4 times because it has 4 different non-equivalent hydrogens within 4 bonds. So even though these 2 are on the same carbon, we will see splitting from that. Okay. So, and just like we saw here, if this was a chloro over here, these are on the same carbon, but they're not equivalent. So we're going to see those split. Okay. And if this is the most common where we have 3 bonds on adjacent carbons. Okay, so now I want to teach you some of the most common splitting patterns so you can recognize these quickly. Okay, so the first one is this right here. And so this means that there's something other than hydrogen, anything other than hydrogen here on all these things. Could be carbons, could be chlorines, doesn't matter. Okay, but if you only have one group here and it has 1, 2, 3, 1 hydrogen adjacent to it, that's going to give a total of 2 peaks. Okay, and now if we look at this side here, we're going to look at this. It has 1 hydrogen within 3 bonds, so we're going to get 2 peaks. So the pattern we'll see is a doublet of doublets. Doublet is 2 peaks, doublet of doublets. Okay, so that's pretty common right there. Okay, so let's look at this one right here. This hydrogen here, right here, this gives us 1 peak and it's within 3 bonds. So it's going to be 1 plus 1 is going to give us a doublet because there's only 1 hydrogen next to that signal. So let's look at the other side here. This hydrogen is one hydrogen, 2 hydrogens. So that's going to be 1, 2 plus 1 is equal to 3. So this is going to be 3 peaks. Okay, so the common pattern is going to be 3, 2. That's telling you that you have those peaks nearby. Do you see what I mean by non-equivalent hydrogens and the hydrogens that are within 3 bonds? Okay, so let's go to this one right here. So this is another very common one, right? Where we have on this side here, we have 2 hydrogens, but we're next to 2 hydrogens. So that's going to be, these are equivalent. So that's going to be 2 plus 1, which gives us 3. So we have a triplet. And the same thing is going to happen on the other side, for this side. So we have 1 peak here, but 2 hydrogens here. So we're going to have 3 peaks here. So we get a set of triplets. Okay. All right. Now this is a very common pattern too. We have CH3 and a CH2. So if we look at this side here, we have 1 peak here plus our 2 hydrogens here. So 1 plus 2 is equal to 3. So this is a triplet right here. And then on the other side here, we have a single peak here, but we have 1, 2, 3. So 1 plus 3 is equal to 4. So a quartet and a triplet next to each other tells us we have an ethyl group. So that's a very common pattern, having an ethyl group on there, hanging off there. Ethyl alcohol, ethyl ester, all those things. And now the other one that's similar to this is we're going to have this peak here only split once, right here. So we have a doublet. And then we have this peak over here is going to be split 3 times. So 1 plus 3 is equal to 4. And we get a quartet. So those are the most common things. Go through the book, and in the homework, you get to do this assignment. And after the quiz on Wednesday, we're going to have an in-class NMR assignment. If you're at home, you can download it off the internet and follow along. Okay. Okay. So let's talk about spin-spin splitting. So in this case here, what we have is we need to look at our equivalencies. So we look at our number of peaks first, and then our splitting second. So in this case here, we have 1 hydrogen here and 1 hydrogen here, but it looks like, I'm sorry, 1 type of hydrogen here and 1 type of hydrogen here. But look, they're the same because these CH3s have the exact same environments as these CH3s. They're both bonded to carbon, and that carbon's bonded to a hydrogen and a bromine. So that means these 6 hydrogens are equivalent. Okay. Now that means that our last hydrogen here is our non-equivalent one. So we have 1 that is different. 1 hydrogen on that one there. So now let's look at our splitting here. Our splitting is going to be, well, let's actually look at our shift first. Is this hydrogen going to be upfield or downfield from the other 6 hydrogens? It's within 2 bonds of a bromine, an electronegative atom. Okay, the other hydrogens are within 3 bonds. So is that hydrogen, the red hydrogen here, the middle one, is it going to be upfield or downfield from those 6 hydrogens? It's going to be downfield because it's closest to electronegative atom. So that means it's going to be this peak down here is going to be our red one, and this peak right here is going to be our blue one, or our other one. So now let's do our splitting right here. So we have a total of 6 hydrogens, and so we're going to do the splitting for them first. And so they get 1 peak for all 6 hydrogens, plus only 1 non-equivalent hydrogen, giving us a 2. So it's giving us a doublet. What if you didn't remember that the shift for the hydrogen would closest to an electronegative atom would shift you downfield? As soon as you did the splitting, you'd have to say, well, this has to be that one because of the splitting. So you can use any of the pieces of information, but hopefully they all add up together. Now let's look at the middle one here. And in that one right here, we have 1 peak right here, but it's next to 6 non-equivalent hydrogens. 6 is equal to 7. So we have 1, 2, 3, 4, 5, 6, 7 peaks. What you'll also see in all NMR spectroscopy is that you're going to have symmetrical peaks. If you have a peak that splits into 2, they're going to be exactly the same height. If you have peak that splits into an odd number, you're gonna have a single peak in the middle, and then you're gonna have this going down in intensity in kind of a pyramidal form. So and then if you had like 4 peaks, it's gonna be 2 there and 2 there that are gonna be 2/3 of the height, or sorry, 1/3 of the height. Okay, all right. So now let's put it all together. Okay, let's put our spin-spin coupling, our shift, and our number of unique pieces together. And let's look at this molecule here. All right. So just from looking at it, how many peaks or types of carbon do we have? 3, because this one is different than that one, and this one has a nitrogen belt on it, so that one has to be up there. Okay, so we have three peaks. Okay, so we can predict what it's going to look like, right? Which one's going to be furthest downfield, A, B, or C? C is going to be furthest downfield, and then we'll have B, and then we'll have A, because this is our electronegative element, our electron withdrawing element, and it gets further away, it affects it less. It's still shifted some because it's 3 bonds away from that carbon and 4 bonds away from there. The shift does go through all the connections. It just less effect as you go further and further out. Okay, so that worked out pretty well. Let's figure out what our splitting pattern should be then. Okay, so we have our number of peaks, we have our splitting. So this one right here is next to 2 hydrogens. So that means it's going to have 3 peaks, right? Those are equivalent hydrogens. They're next to 2 hydrogens. There are no hydrogens on this side. So we're going to get 3 peaks. Okay. So let's look at this one right here. So that's 1 signal plus 2 on this side and 3 on that side. So 1 plus 5 is equal to 6. So we're going to have 6 signals here. Ooh, that's neat. So we should be able to find those just by looking at those. And let's look at our last one right here. We have 3 right here, but they're all the same. So that's 1 signal next to 2 hydrogens. So that's going to be 3 as well. Okay. So we've already predicted what it's going to look like. Then we can also predict what our integration should be. Our integration should be 3, 2, and 2 because of our number of hydrogens on each of these. So we can use any of this information to help us figure out where everything is on the spectrum. So if we look at that right here, we predicted that C would be furthest downfield, and it is, followed by B, followed by A. Okay. We predicted that C would have a triplet, and C has a triplet. We predicted that there were 6 on here, and we have, notice 1, 2, 3, 4, 5, 6. Notice how they're even at the top, so you know it's an even number. And if they have 1 in the middle, that means it's an odd number. And we predicted 3 for this. And if we did integration, we would see a 2, 2, 3. Okay. See how this works out, where we can actually get a prediction just by looking at the molecule and then start to look at the spectrum. Okay. Now, if you looked at a spectrum first and tried to figure out your molecule, what you would have to do is say, okay, well, this is hooked to that because of the splitting. This is hooked to that because of the splitting. And this is closest to the electronegative atom. And this is further away. Okay. Questions on spin-spin coupling? Okay. Oops. Okay. All right. So now there's one rule we got to remember. Spin-spin coupling does not happen. Spin-spin coupling does not happen through an oxygen or a nitrogen. Okay. Does not couple through an oxygen or a nitrogen. So here's an example of that right here, where we would predict it to be this one right here would be a triplet because of the 2 hydrogens here. This one right here would be 1, 2, 3 plus this one over here. So 4, so that should be 5, but it's not. It's only 4. Okay, because we cannot go spin couple through oxygen. You can only spin couple through carbon. Okay, so what we see here is then we're going to get a total of 1 peak, 2 peaks, and 3 peaks. And this one's going to be a singlet. And this one's not going to be 5, it's going to be 4. So if we look at our thing, we get a single peak for the alcohol, 4 peaks for the carbon next to the alcohol, and 3 peaks at the lowest or most upfield. Okay. So the other cool thing about this is any acidic hydrogen here can exchange out with deuterium. And so if we had deuterium water, which is the higher isotope of hydrogen, they'll exchange. And what will happen is deuterium is not, you can't see it at this frequency. And so what happens is it disappears. So if you're not sure if you have an alcohol, you can put a drop of water and watch the intensity of that peak decrease. So this peak would go away and you would only have the 2 other peaks. Okay, so that's really, really important there. So we're gonna, we're gonna stop here. Actually, I'm gonna do benzene on next week. I'm sorry, Wednesday after our quiz. Okay, so next week we're going to do a quiz. We're going to, Wednesday we're going to do a quiz. We're going to finish proton NMR. We're going to do a proton NMR activity, and then we're going to start on carbon NMR. And I have a carbon NMR activity after that. Okay, so the activities are going to be like predicting what it should look like and picking the right molecule out of a lineup. So it'll be kind of fun. All right, any questions from, okay, I got a thumbs up online, so that's good. All right, so I'm gonna go ahead and stop sharing and stop recording.